There is a wooden box. It is roughly the size of a stereo speaker. The inside is painted flat black. The front is covered in glass. When you mount it in a south-facing window on a January morning, cold air enters through a slot at the bottom, slides across that black surface, and within minutes begins climbing back into your living room at 120 degrees Fahrenheit. No motor turns, no fan hums, no wire connects it to anything. The sun does the work, the physics does the rest, and your furnace cycles less. Total cost of materials, depending on what you scavenge, runs between $20 and $100. The plans have existed for over 50 years. They are not classified, not patented in any restrictive sense, not buried in obscure journals. They sat on the cover of Mother Earth News in 1977. And yet, walk into any Home Depot in the United States today and ask a clerk where to find a window box solar heater. You will get a blank stare. This is the story of a device that should be on every winter-facing window in the United States, and the strange and entirely explainable reasons it is not. The principle is called thermosiphon. It is the same convective loop that moves warm air to the ceiling of your room and cool air to the floor. Inside the box, sunlight passes through the glass front and strikes a dark absorber. The absorber can be a sheet of metal, a stack of cut soda cans, or a corrugated panel painted matte black. That absorber gets hot, and the air immediately surrounding it gets hot. Hot air rises. It exits through the upper vent and enters the room. As it leaves, it pulls cooler room air in through the lower vent. That cooler air slides across the absorber, heats up, and rises in turn. The loop is self-sustaining as long as the sun is shining. When the sun sets and the absorber cools, the air column inside settles and the loop stops. A simple flap or a backdraft damper prevents cold night air from flowing in reverse. There is no thermostat. There is nothing to fail. There is nothing to maintain except the glass, which you wipe with a rag. The performance numbers are not folklore. Peer-reviewed engineering studies on aluminum soda can absorbers, the cheapest version of this design, have measured thermal efficiencies between 40 and 86%. Optimized arrangements with cans angled diagonally to extend the air's contact time have hit nearly 98% in laboratory testing. A standard 4-foot by 8-foot collector produces between 1,000 and 4,000 BTU per hour at peak sun. Output air temperatures regularly reach 120 to 128 degrees Fahrenheit on clear winter days, 50 degrees above the ambient room temperature it is feeding back into. Real owners who have run these units as supplemental heat report 20 to 50% reductions in their winter heating bills. The University of Washington. Bothell Tiny House Project added a soda can collector to one of its structures and recorded a contribution of 2,246 BTU, covering nearly half the heating demand of the entire building. The history is where the story turns strange. In 1969, a man named Steve Baer founded a company called Zomeworks in Albuquerque, New Mexico. Baer was a self-taught engineer with a fondness for geodesic geometry and a deep impatience for mechanical complexity. His home in Corrales, New Mexico, built in 1971, used drums of water stacked behind south-facing glass to absorb heat during the day and release it at night. That house still functions on his original systems more than half a century later, with no significant modifications. Baer held more than a dozen patents on passive solar mechanisms. He demonstrated, repeatedly and publicly, that 75% of a conventional home's heating load could be replaced with sunlight, water, glass, and gravity. He was not the only one. The physicist William Shircliffe, working out of Harvard, refined Baer's concepts into formal engineering specifications and published them widely. Mother Earth News popularized a particular variation called the heat grabber, with plans simple enough that homeowners reported building functional units in under an hour. That hour mattered, because in October of 1973, OPEC announced an oil embargo against the United States, and the price of heating oil rose 350% in 18 months. Americans, suddenly facing winter heating bills they could not afford, did what Americans do. They built things in their driveways and garages. The federal government printing office, then operating with an actual mandate to inform the public, distributed plans for window box solar heaters at no cost through the Department of Energy. Tens of thousands of these units went up on suburban windows across the country between 1974 and 1980. Solar industry employment peaked at 30,000 American workers by 1980. Tax credits, federal research grants, university programs, and a national mood of energy independence created an ecosystem where a wooden box that heated a room with sunlight was treated as a perfectly reasonable thing to install on a Tuesday afternoon. Then, in 1986, the Reagan administration allowed the federal solar tax credit to expire. Within 2 years, the residential solar industry had collapsed. By the 1990s, the technology had effectively vanished from mainstream construction discourse. Not because it stopped working, not because anyone disproved the physics. The physics is the same physics that warms a parked car in February. The reasons it disappeared from American homes are economic and regulatory, and they are worth examining closely because they explain a great deal about why simple solutions to expensive problems so often fail to reach the people who need them. Begin with retail. A $20 plywood box cannot support the markup chain that makes a product profitable to distribute through a national hardware chain. Marketing, packaging, warehousing, shelf space, sales staff, customer service, warranty fulfillment, and returns handling each take a percentage. By the time a product reaches a Home Depot shelf, it typically needs to retail at 3 to 5 times its raw materials cost just to break even for the retailer. A window box solar heater that costs $20 in materials would need to sell for $100 at minimum. At that price, the homeowner is better off building it themselves. Most homeowners will not build it because they did not know the option existed. That is precisely why it is not on the shelf. The chicken and the egg sit in the same dark corner of the warehouse. Then there is the warranty problem. A passive solar air heater's performance depends on factors entirely outside the manufacturer's control. Latitude, weather, window orientation, tree shading, snow cover, and critically, the type of glass already installed in the host window. Modern low-E windows, which now dominate American residential construction, are coated specifically to reflect infrared radiation, which is exactly the wavelength range a solar absorber needs to capture. A window box mounted behind a low-E window operates at 40 to 65% of its rated output. Double and triple pane configurations compound the problem. An honest manufacturer cannot guarantee any specific BTU output without first inspecting the customer's home, and that level of pre-sale engineering destroys any retail margin that might have existed. The HVAC industry has its own reasons for treating this technology as if it does not exist. The American residential heating and cooling market generates $94 billion annually in equipment sales, installation labor, service contracts, and refrigerant. A wooden box that requires no installation crew, no annual service visit, no filter replacement, no refrigerant top-off, and no eventual compressor failure is, from the perspective of that $94 billion industry, an active threat. The Air Conditioning Contractors of America has historically lobbied against the inclusion of passive solar credits in residential building codes. Building inspectors, by training and by trade certification, are equipped to evaluate mechanical systems with measurable inputs and outputs. A non-mechanical heating contribution, no matter how real the BTU output, falls outside their evaluation framework. The regulatory environment finishes the job. Most American building codes treat any exterior window-mounted device as a structural modification requiring permits, engineering review, and inspection. Homeowner association covenants across the country explicitly prohibit visible solar collectors. The International Residential Code, which forms the basis of most state and local codes, contains no compliance pathway for passive air heaters. State energy efficiency tax credits flow exclusively to mechanical heating systems and photovoltaic panels with certified output ratings. Some homeowner insurance policies classify modified windows as policy violations. Compare this to Europe, where the same physics receives entirely different treatment. German passive solar building codes reward window-integrated air heaters with formal energy credits. The Austrian Passive House standard, now adopted across the European Union, incorporates tram walls and air collectors as baseline architectural assumptions. The Swiss Minergie certification system documents measured thermal output from thousands of installed units. Northern European homes routinely achieve 30% heating reduction through passive solar air collection, and the regulators, builders, and insurers all treat this as ordinary engineering. American building science, working from identical physics, treats the same approach as fringe technology. There are commercial versions on the American market for those who want one without the saw. Northern Tool sells a production window box heater for $249. Amazon lists Chinese manufactured units between $200 and $400. A Canadian company called Your Solar Home has produced commercial units since 2008. Sales remain marginal because, as a supplemental device, the payback period exceeds 5 years, which is too long for retail consumers and too short for the recurring revenue models that drive the heating industry. For the builder, the construction is straightforward. A basic frame is assembled from 2x4 lumber into a shallow rectangular box. The interior receives a coat of high-temperature flat black paint, or, for the ambitious, a selective absorber coating now sold at specialty hardware stores at prices that match aerospace-grade performance from 20 years ago. Aluminum soda cans, cut top and bottom and stacked vertically, create an absorber matrix with enormous surface area. Polycarbonate or tempered glass covers the front. Foam board insulation lines the back to prevent heat loss into the wall behind. Total construction time runs 4 to 6 hours for a competent builder working from any of the freely available plans. No electrical work is required. The unit mounts on exterior brackets with 2 vents penetrating the window frame. The honest limitations matter. This is not a furnace replacement. It only operates when the sun is shining, which means overcast stretches produce minimal output exactly when heating demand peaks. A south-facing window without obstructions is mandatory. A poorly sealed installation can develop condensation and mold within months, which is the single most common failure mode reported in the field. This system supplements a conventional heating system rather than replacing it. But supplemental is not nothing. 20 to 50% reductions in winter heating costs, applied across a country that spent over $140 billion on residential heating last year, would be an enormous reduction in fossil fuel consumption, household energy expense, and atmospheric carbon. It would happen with no grid upgrades, no battery installations, no rare earth mining, no subsidy programs, and no technology that does not already exist in your garage. Recent peer-reviewed work on reduced graphene oxide nanoparticle coatings has pushed absorber efficiency up another 23%. V-corrugated absorber plates outperform flat plates by 35%. A 2025 design with 7 movable absorber plates set new efficiency records. The technology is improving even as the country pretends it does not exist. The reason these heaters are not at Lowe's is not conspiracy. It is something simpler and more difficult to dislodge. A $20 solution cannot survive the markup chain that makes products profitable to distribute. A device that needs no service cannot support a service industry. A modification that escapes the inspection regime cannot be permitted under it. The physics is settled, and the economics is hostile. The sun has been waiting above your house every winter for as long as the house has stood, and it will continue to wait, free for the taking, for anyone with a saw, an afternoon, and a south-facing window.